Can I see this? Oh, I cannot see.
It's
It's
just
not
that
possible.
one screen, and now you have to also on the window. Nothing else.
So it's going to be a little complicated to look at you and at the presentation, but let's start. Actually, I have two presentations. One is the Prezi presentation, and one is the PowerPoint presentation that goes more into detail. The first part is just presenting what MeshPath is doing, what are our products and our vision. Let's start with our vision. As you can see, our vision is to simulate machine tools, machines. And our vision is to have a virtual simulation model of each single part of each manufacturer. I'm talking about mechanical parts like linear guides and ball screws and bearings and so on, drives. And secondly, our vision is to have a component-oriented finite element simulation software for all machine manufacturers. And I'm going to present the software and the library in the next steps. Here is just a small video. This video is showing the basic idea behind our software. So here you have different finite element models. And you can pick up those models from our library of simulation models and assemble them like you would do this in a CAD system, right? And you can build up very big assemblies of structures just like in a Lego play. And then you can compute, like here in this case, vibrations of the machine, which are very important for the.
What's ticking, what's decay, what's else?
Everything here is TCL. So what you saw is done. I mean, everything you will see is TCL. So it's about TCL at MeshPath. So.
Okay, mouse is still on my screen.
Okay. Let's go back. About us. MeshPath is a fresh, small company located in Stuttgart, founded 2013 with 2 people. Right now, we are a bigger team. We are 4 people, and we are planning to grow. Probably until the end of the year, we'll be about 10. And we are looking forward to expand our team. So we actually also need new team members. I also search for somebody that can program in C, C++, and TCL. How we started? Well, the starting point was a research institute. The so-called ISW. This is a research institute in Stuttgart about machine tools and control of machine tools. This is actually where I started as a student and later as a research employee. So the whole idea sparked actually as I was a student, this idea of having component-oriented finite element modeling. And during my research at the University of Stuttgart, I developed tools in TCL to make this possible. And 2012, I decided to start my own company, and MeshPath was founded 2013. And 2014, we had the first release of our software, which is the first and only component-oriented finite element software. And moving forward to simplifying simulation, we actually doing right now other stuff. We are also doing the so-called web applications, where actually you only have to input parameters of some standard models, and you can get your simulation report from the web browser. So you don't need any knowledge about simulation. But behind the scenes is still our software. So behind those web applications. So this is how we started. Our strategic positioning is when you look at the market, you have this positioning here. On one side, you have the expert software, which makes possible to deal with high complexity of modeling. But the drawback of this expert software is that you cannot do a lot of high number of design variants. So if you want to study design changes in your product, it's going to be difficult. And on the other side, you have this basic simulation software, which don't really allow you to do complex things, but it's really fast, and you can do design changes very fast. And MeshPath is positioning on the right upper corner, where you can deal with high complexity, and at the same time, you can generate a big number of design variants in a very short time. So this is our strategic positioning. So complex, large finite element assemblies and high number of design variants with minimal effort. This is our target. So let's go back to what we do in a more concrete way. We have this really awesome component-oriented software, which is almost completely programmed in EuroTcl, and we have the whole software is backed by a very impressive amount of simulation models inside of a library, which is available online for everybody to use. And I will show you some example of our parts library. Those are the typical models inside of this library. Those are mechanical parts, and they really have this mechanical behavior. For example, if you have a gearbox here, then this gearbox will be able to behave like in reality with stiffness and transmission ratio and so on. So everything comes as a ready-to-use simulation model. We do this for all the typical manufacturers of components, and currently we are extending the number of manufacturers having those libraries in our having their components in our library. So if you want to think of it, it's like the CAD parts libraries, but it's not CAD, it's finite element simulation. Okay? And the concept is that we develop those libraries with the help of parts manufacturers, and the machine manufacturers, which are customers of the parts manufacturers, can get those libraries and actually use them in their design. So this simplifies the design process dramatically. Then this is a screenshot of our UI of the software, which is programmed in, like I said, in EuroTcl. And this software is used mainly by machine manufacturers currently. We actually also look forward to expand the usage of our software, not only in the machinery industry, but also in other areas. But right now we are focusing on that. And the software is also a back end of the simulation apps, which run in the browser. And this software allows you to robustly automate the model generation process. I will show this later. This is just an introduction, and I will also say a few words about our simulation apps. This is typical UI of the simulation app, where you can just input your parameters and then hit the send generate report simulation, and at the end you will get a simulation report of your product. But this is not the focus today. Today we are going to talk about the software. So I will skip this simulation app thing, but you can read more about that on our website if you have interest. So I will switch now to my computer because it contains the PowerPoint presentation and the software. So this is a more detailed screenshot of the software. As you can see, it's fairly complex. At the same time, it's easy to use. We have a I just want to highlight the packages that we are using there because, of course, we have developed a lot of code, but at the same time, we are using a lot of those free packages that are available to the EuroTcl community. And one of the main packages here is tree control and shell icon, which allows us to make those nice looking trees here. For example, one that really looks identical to the Microsoft Explorer tree, and another one that contains or displays the model structure, which is the so-called model tree. Secondly, we are using the great TCL3D package of Paul Obermeier, which allows us to really, thank you, which allows us to do very fast displays of large models. Then we are also Paul Obermeier code, especially the Excel integration that allows us to read Excel files and display the content of those Excel files. The C-text and the text widget and the C-text, I'm looking forward to get the improved version of text, and because we are using this a lot. And also the table list of Saba. Thank you, Saba, again for your update. Those are the main packages, but actually we have a total of 30 external packages used by our application in order to make this software possible. So this is the complete list of our packages, external packages. I would like to show a little bit before I will go and really show you the software. I would like to explain how our communication architecture is set, because we are also we have this software, the MeshPath software. It can be run both as a client or as a server. So it's the same software. You just start it with a specific flag, and then it runs in server mode. So you can put it on any web server, and it will allow you to communicate through an Apache server with the software and basically do cloud computation. So this actually simplifies a lot of the development process because we don't have to have scripts on the server and scripts in the software. It's the same thing. So this is the structure we have. Imagine you as a client, you are using our software, and what you want to do is to let's do some computation or download some simulation part or generating some simulation parts on the server. And what will happen at the client software will communicate through HTTP and TLS with our Apache server. And the Apache server builds a socket connection with the same software, but in server mode. And the software will do your request, whatever request that is. And on the other side, we have this MeshPath library of simulation models. So this is hosted on our server. You can download those parts through this chain here. And the client software will download those parts and save them in your local library of simulation models. And at the same time, you can create your own libraries of simulation models that are not on the server and put them in the same library. This is the concept of the simulation architecture. I will switch now to the simulation software because I also have a wish list, but I would like to show this at the end. Let me start it.
This is the budget or SVM.
This is Git.
Okay.
This is Git. Yeah.
So only overlay that
I think also my computer is a little slow. We saw that the difference.
Maybe if you minimized the big window, then we would see the splash pan. Ah, okay, well.
So, let me hide the taskbar. Okay. So the screen is a little small, unfortunately, but I hope it's possible. Yeah, it's okay. So the first step is what I can do is to log in into the software. The whole licensing management is done by our server. So when you register and download the software, you can log in with your email address and password. After that, the software will show you a history preview of your models. And what I did, because of the previous talk about the bike frames, and I tried to have a starting point for a bike frame, but I didn't finish. So it's not so impressive. Let me hide this. So what we have here is basically two tubes. People that are used to those to bikes perhaps will recognize we have here the head tube and the top tube, and this is where you sit normally, and this is where the fork comes in, right? And I think this MeshPath would be a really ideal tool to take the parameters from the bike frame app and transfer those parameters to our software and generate a whole bicycle model for the simulation. It can be done completely CAD-free, so you don't need any CAD import because our models are parametric and CAD-free. So we actually generate finite element models directly, not CAD geometry. But still, I mean, if you can see if you select a surface here, our software will tell you that this is a cylinder, although there is no CAD geometry behind it. It's just a mesh. So the software identifies geometries from the mesh, from the point cloud. So it's parametric. If you click on one part here, then it will show you the part parameters. And for example, the head tube length is here defined, the diameter of this tube, and the wall thickness. Right? And also you have things like mesh scaling factors. You can refine the mesh. For example, if I want to have a finer mesh here, I can take another factor and then say generate. It will take a while to generate the mesh.
In the meantime, I want to ask a question.
Yeah,
how
please.
How did you do the metering at the surface of the top bar where it touches the vertical, the cylinder?
I will come back to this later. This is something regarding the second tube here, the top tube.
Okay, so
it has a parameter that says, okay, this tube will have to be connected to a head tube having this diameter.
okay.
So I'm telling to this part already which is the diameter of the connecting part, you know. So when I'm generating this, I'm doing basically a Boolean operation of subtracting the head tube from the top tube, and then you will get that. Exactly, yeah. So you can see now we have a finer mesh here, yeah, just by changing that parameter. You can also, I mean, the whole thing is assembled here. It has positioning constraints like in a CAD model. For example, the distance between the top tube to the bottom is here defined. So, for example, I can change that here. You can see how easily you can adapt parameters. And the whole thing, I mean, right now I'm entering a number here. But if it's a parameter name, then it's no problem, because in MeshPath, everything you enter is or can be a parameter. So we can fully parameterize the whole assembly. And after assembling this frame, we also have connections. So you can see here, for example, that this surface here, the red mark surface, is connected to the green one. So that we really have a physical connection here. This is something you, in the finite element world, you really have to specify, because only geometric coincidence does not mean that we have mechanical coincidence, so mechanical connection. So that's why we have those connections here. And going forward to the top tube, you can see the top tube has also the length here, its own diameter, the wall thickness, and then we have some parameters regarding the head tube. So the head angle, the seat angle, the head tube diameter, and so on. And also for the second end here, we also have the seat tube angle and diameter, which defines the geometry here at this end. So now we have the geometry. Let's imagine the whole frame would be finished now. No? It's not, but it's just a to-do for me. So it's actually pretty simple. Let's suppose we have all those things. What we do now is to select surfaces and say, okay, this surface is fixed, for example, and at this end we have a force acting, right? You can set up the amount of force. You can also apply into different directions here, as you can see, right? That's it. If you are done with your parameterization and boundary condition definition and so on, you can say, okay, now I want the solution of this. I want to compute the solution. So you click on the solve button, and the whole assembly will be now solved. It takes a few seconds, probably. So right now you can still do other things and interact with the model while the solution is done. But right now it's a little bit busy because it downloads the result files.
So the solution was computed on the server?
Yeah.
Why isn't the solution produced on the computer? Is it too weak?
Well, I don't have the solution. The software only does modeling and post-processing. The solution is done with third-party software. We don't implement the solvers for the finite element solution. So it depends what you have on your computer. If it recognizes a solver, then you take that. But we don't have a license for our solver on this laptop. So the software automatically switches to the server and does this.
Kind of a batch processing. Just kind of
It's like a batch processing. Yeah, exactly. So this is what this is the reason why I talked about the architecture, because it's a dual architecture. I can just have this software on another computer, the same software, no change. Just when you start it, you place this flag for server mode, and then you also need an Apache server that will communicate through sockets with the software, and that's it. So you have a cloud computation solution by doing that.
Could it use more machines in parallel too, or does it just, could it also do some load sharing among?
Yeah, you can. Yeah, it has multiple threading, so multiple users can work at the same time on the server. Yeah, yeah. So right now it says the solution is done. Just click visualize results. I'll do that. So now you have the deformation of the model. You can also animate the result. We are still looking to improve the performance of the visualization. It's, in my opinion, a little bit too slow, but the reason for that is that we are not using a C function for that. So we did a fast implementation of the visualization in TCL, but one of the tasks would be to really replace it by a C function, and then it will be like 100 times faster.
Or hope for quad code that it will be also.
Or like that, yeah. I mean, this is also, but once the computation is done, once the display lists are there, you can, it's actually pretty fast in displaying. So this is not a problem. Display is very fast. You can also, actually, the nice thing about MeshPath is that you can drag your components away, and you can look into detail what happens with your frame. So this is a very simple model. It can be extended to any structure. I mean, we can also add bearings to this head tube here, and the fork, and so on. So that's not a problem. It's just something that could be done, yeah. And yeah, the software is actually, I mean, we are using this for very large assemblies. I mean, this is just a small example, and right now I think that's a good idea to demonstrate this. I will open a larger assembly. Let's open this one, and in the meanwhile, I will continue with my wish list. This actually not, I mean, this is not really, those are things that we need in our software. Those are small things, but as always, small things matter for the customer. So it's always about the detail. We talked yesterday about at the evening event that it would be nice to have a fuzzy string comparison in EuroTcl. And Christian said to me, this is the Levenstein algorithm. The Levenstein distance, right?
Similar. Okay.
So it's like the Google does the search, right? If you only know the end of the word or the start of the word, or you misplace the letter, it will still find the right string for you. So we need that, for example, if we want to do a fast search in our model database. And we think that a string compare minus Levenstein option would be a good solution for that. Also, a string compare dictionary would be something that should be implemented. Then, one big wish of mine, yeah.
What the dictionary string compare to?
Like L-sort minus dictionary.
Yeah.
You have L-sort minus dictionary, but you do not have a string compare minus dictionary. And that's really annoying, because if you have
I still don't yet get the concept
L-sort.
of it. L-sort. This dictionary. Okay.
You have L-sort minus dictionary. And if you do L-sort minus command, and in the command you want to resort to minus dictionary, you can't do it. You have to compare two elements with minus dictionary. You have to do a list, sort that, and compare it to the first element. And that is really...
that one, I think, would be a reasonable one to put in. Whereas the Levenstein distance computer, I think that feels a bit more like something that belongs as a library function, not as a...
Well, yeah.
It's not to say that it shouldn't be done in a way that is fast. It's just that that's a major extension by comparison with taking functionality that we have in one spot and making it so that it's more consistently available.
Yeah. Okay, so the one next wish of mine would be to have the standard bindings that are common to all text editors in the world, to have it also as a standard binding in the text widget. For example, just small examples. If you press down the control key and then the backspace, that will delete the whole word in front of the cursor. Or if you press the control key and the left and right arrows, the cursor will jump to the beginning or end of the word Double click a word would have to select the word but ignore the special signs like equal and so on. This is not happening right now. And also basic things like Control A should select the whole text. I think this behavior should be standard out of the box with the text widget. And another thing is grouping in the TCL in the combo box. For example, in our software we have this large list here, and as you can see, some items are actually the same, are groupings. So having a meaning of having separators in the combo box, or perhaps the first word in the group as a bold character, I don't know, something like that.
Limitation in the UI, if you have the standard Win32 controls, you have really limitations, and so if the TK widgets based on Windows, for example, on
probably
standard controls, you won't be able to implement it in a very simple way.
Okay.
So it would be a lot more complicated.
Okay. Good. Okay.
Yeah.
Yeah, I'm almost finished. One issue I have is I will show you in the software. This is the last slide. No, the software is still loading.
Okay.
I think it's the network because it communicates. Okay, never mind. Perhaps I will show this another time. I think this was my presentation. If you have any questions, please ask. Yeah.
If you get parts from manufacturers, how do you get your parametric models from this part? Because they come from a CAD system, they are perhaps from Parasolid or other core technologies. So how do you get your parametric?
Well, if necessary, I mean, most of the time, parts for the simulation must be simple. So we actually don't need all the details of a CAD model. But on the other side, there are parts where we need a CAD model, and then in that case, we just add those CAD parts to our library and import them. Okay. You know, just automatic CAD meshing and extending the CAD model with the features that the simulation needs is done automatically. Okay. So we have our scripts that do that.
Do you have perhaps we have to talk later because we are late.
Yeah,
Because
maybe.
I have some question about can support eventually deflection, path
I would
deflection.
think you can.
We can talk later, yeah.
Next break.
Yeah. Yeah.
So, Alexandru, thank you.